All right, so these stones or stone tools from an archaeological site in Cactus Hill, Virginia, are at least 15,000 years old. Scientists estimate the age of the site based on the rates of nuclear decay. How do nuclear decay rates differ from chemical reaction rates? Unlike chemical reaction rates, which vary with the conditions of the reaction, nuclear decay rates are pretty much constant. Half-life. So I'm gonna front end load on this. Nuclear decay. We just learned yesterday about alpha and beta particles and gamma rays. But the sun bombards the Earth with particles, and sometimes those particles wedge themselves in the atoms of the elements. And so we know, for example, carbon has 6 protons, 6 neutrons, but sometimes they can have extra, and it's still carbon. They might have 6 protons, but they might have 2 extra neutrons, and so on and so forth. Well, they don't belong there. And if you go all the way back to one of our first, remember when we built atoms on that virtual lab? How the number of neutrons and protons and electrons can make the atom unstable? Well, the atom wants to be stable. So what it does is over time, it just emits the extra stuff that it doesn't need. And we call that nuclear decay. So the half-life is the time required for 1/2 of a sample of a radioisotope to decay. After one half-life, half of the atoms in the radioactive sample have decayed, while the other half remains unchanged. After 2 half-lives, half of the remaining isotope decays. After 3 half-lives, the remaining fraction is 1/8. Okay? So a half-life is the amount of time it takes for half of the radioactive material to decay to half. Okay? So the half-life of beta decay of iodine-131 is about 8.07 days. So after 1 half-life, it goes from 100 to 50. That's 8.7 days. After 2 half-lives, it goes to 25, which is 1/2 of 1/2, or 1/4. After 3 half-lives, it's 12.5, which is 1/8 of 100. So we're just 1/2ing every half-life. So from here to here, 1/2. From here to here, 1/2 of where we started. And 12.5 is 1/2 of 25. So 100, what's 1/2 of 100? 50. What's 1/2 of 50? 25. What's 1/2 of 25? 12.5. And on the 4th half-life, it should be about 6.75, something like that. Okay? And that's how it works. And what happens is the radioactive material, so this is what they're saying is iodine-131 will decay and then it becomes another substance after it emits the extra nuclear material, whether it's an extra neutron or whatever. Okay? So every radioisotope decays at a specific rate. Half-lives can vary from fractions of a second to billions of years. So these are the different things that are emitted: alpha particle, beta particle, gamma ray, alpha, gamma ray, beta particle, alpha particle, gamma ray. And we talked about this yesterday, but I don't know if you guys figured this out exactly. Hold on one second, I gotta take this. Hey, did you just call me? Okay. I'm leaving it in the video so people could see how hectic teacher life is. All right. That was a wrong number. So anyways, these are the particles. This is the Greek letter alpha. This is the Greek letter beta. And this is the Greek letter gamma. So alpha particle, beta particle, gamma ray. Okay? The amount of time that it takes for the half-life, as you can see, could be billions of years. So uranium-238 takes a long time. Okay? Radon, Very little time, 3.82 days. Okay. Carbon-14 is 5,730 years, and it emits beta particles. So how does that work? Well, let's look at an example. Iridium-182 goes through beta decay to form osmium-182. The half-life of iridium-182 is 15 minutes. After 45 minutes, how much iridium-182 will remain in an original 1 gram sample? So you're just going to take the total time of the decay and divide it by the half-life, and that'll tell you how many half-lives that you go through. Once you know how many half-lives, you're just going to say 1/2 raised to whatever that number is. So this would be 1/2 raised to the third power, or 1/2 times 1/2 times 1/2, which is 1/8. So after 45 minutes, 1/8 of a gram, that's what 0.125 is, will remain. Now, what does that say about the rest of the stuff? Well, the rest of the stuff is decayed and become another substance because it's emitted beta particle. Anybody in here remember what a beta particle is? All right, we'll talk about that some more. How do scientists determine the age of an object that contains carbon-14? In radiocarbon dating, the age of an object is determined by comparing the object's carbon-14 levels with carbon-14 levels in the atmosphere. So carbon-14 can decay to nitrogen-14 plus the emission of a beta particle, right? So remember, a beta particle is just kind of like a negative charge. It's almost like an electron, right? Just emits an electron. So, kind of. So anyways, the artifacts of Cactus Hill were dated by using carbon-14 dating, which has a half-life of 5,700 years, basically. Carbon-14 is formed in the upper atmosphere when neutrons produced by cosmic rays collide with nitrogen-14 atoms. Carbon-14 undergoes beta decay, and it forms nitrogen-14. So if you look on the periodic table, you have nitrogen, which is just one group to the right of carbon. So they're very similar. So plants absorbing carbon dioxide during photosynthesis make the same ratio of carbon-14 to carbon-12 as in the atmosphere. Animals with the same ratio of carbon isotopes as the plants they eat. When a plant or animal dies, it is no longer able to absorb carbon, right? So this carbon comes from the atmosphere. The atmosphere, the soil has that type of carbon. Carbon's carbon. And so the plants will have a certain level of that carbon. That's how that type of carbon gets in our body. We digest the plants, whether we eat meat or not. Let's say you eat chickens. Right? The chicken's going to eat some sort of vegetation that has carbon-14 in it. That means it'll have carbon-14 in its meat. When you eat chicken as a meat, you're going to ingest carbon-14 in your body. So there's a percentage of carbon-14 and a percentage of carbon-12 inside your body. And all organic materials, living organisms, have carbon in them. So after you die, though, you don't ingest any more carbon-14. And over time, the carbon-14 decays to nitrogen-14. Does that make sense? And when you compare the levels of carbon-14 with regards to the percentage of the carbon, that you can use that mathematically to work backwards and figure out how long this organic material has been not living. So if the ratio of carbon-14 to carbon-12 in a fossil is half the atmospheric ratio, the organism lived 5,730 years ago. Because the atmospheric carbon-14 levels can change over time, the calculated age for a fossil is not totally accurate. There's a lot of assumptions made. on that ratio. You're assuming that the sun has bombarded the Earth with these neutrons at a constant rate for millions of years, right? We don't know that for sure because we weren't here millions of years ago. So it's an approximation for sure. Because the atmospheric carbon levels can change, to get a more accurate radiocarbon date, scientists compare carbon-14 levels in the sample and carbon-14 levels in objects of a known age. So if they know something is so many years old, they say, well, where's that at, right? So you might say, well, how do they find out? Well, there are structures that we know when they were built, and they had organic material in them, which means they have a certain percentage of carbon-14, right? If something was made with wood 5,000 years ago, 10,000 years ago, and we still have access to that wood, we can approximate based on the levels of carbon-14 in that wood and compare it to the carbon-14 levels in another artifact. So radiocarbon dating has been used to date containing an object less than 50,000 years old. Okay. Objects older than 50,000 years may contain too little carbon-14 that's even measurable. After 50,000 years, that's 10 half-lives approximately, or 9 half-lives. So 1/2 raised to the 8th is like 1/32. That's not a lot. Okay. Radiocarbon dating helps archaeologists learn more about ancient civilizations. This Egyptian mummy case containing the remains of a cat is 1,900 years old. Now, if you've ever been to the Field Museum in Chicago, they actually have like an Egyptian display there, and they have these mummified cats. It's really kind of a cool thing to see. But they know in human history how old this cat is, and then they can compare the carbon-14 dating to that. Just a couple quick questions. If cesium-137 has a half-life of 30 years, and you find a sample with 3 grams, how much cesium-137 would there be after 90 years? Well, it'd be 1/2 times 1/2 times 1/2, right? Because that's 3 half-lives. So that'd be 1/8 of a third, right? Or 1/8 of 3. Let me read this again. Has a half-life of 30 years. You find a sample with 3 grams. Oh, no, you got to go the other way. So you double it 3 times. So they're saying it has a half-life of 30 years. If they think that it existed 90 years ago, how much did it originally have? So you do the opposite. You would double it. So you would say 2 times 3 is 6. 2 times 6 is 12. 2 times 12 is 24. Get on my level. Okay. What factors influence nuclear decay rates? What do you guys think? Do you think it's pressure? You think temperature can have an impact? Concentration? Number of neutrons in the nucleus? Number of neutrons. The extra neutrons is what makes the atoms unstable, and that is what doesn't belong. What radioisotope is most commonly used to determine the age of artifacts made of wood? Carbon-14. It's an organic material. It uses carbon. Remember that glucose is carbon, right? And that's it. Any questions?